We're going to start talking about sets, and because we're just beginning this topic, you'll find that we have a lot of definitions to talk about. So if you feel the need to stop the video, to write down the definitions and really think about what they mean, don't forget that you've got that opportunity to just pause the video and really give some thought to what we're talking about. So a set is just a collection of objects. Now that could be a collection of any objects, and this isn't really an idea that's new to us. For example, the tires on your car are called a set of tires, or the dishes in your kitchen are a set of dishes. So generally speaking, a set is just a collection of objects that we're grouping together for some reason. An element is an object contained within a set. So if we're thinking about the tires on our car as being a set of tires, we could say that your car's left front tire is an element of that set. A finite set contains a countable number of objects. So if we think about the car example again, the car has 4 tires. We can count the number of tires on the car. So the set of tires on the car are a finite set. On the other hand, an infinite set contains an unlimited number of objects. So an example of an infinite set might be the counting numbers being the numbers 1, 2, 3, 4, and so on, and they continue forever in that pattern. So because they continue forever and we can't have a specific number that represents the number of counting numbers there are, the counting numbers make up an infinite set. A cardinal number is used to count the objects in a set. So if we think about the letters in the alphabet, we could say that the number 26 is a cardinal number because 26 represents the number of letters in the alphabet. On the other hand, an ordinal number is used to describe the position of an element in a set. So if we think about the letters in the alphabet, we could say that the letter D is the 4th letter of the alphabet. So 4th is an ordinal number. So generally speaking, those ordinal numbers are the numbers that have the THs after them, the STs after them like first, or RD like third. They're representing positions of elements within a set. Now, 2 sets are considered equal if they contain exactly the same elements, but those elements can be in any order. So if we look at these 2 sets, the first set contains A, R, T, and S, and the second set contains S, T, A, and R. These 2 would be considered equal sets. They have exactly the same elements, even though the order is different. Now the notation that we use for equal sets is familiar. It's an equal sign. So if we write A equals B, that means the set A and the set B are equal. They contain exactly the same elements. On the other hand, equivalent sets are sets that contain the same number of elements, but the elements don't have to be the same. So if you look at the 2 pictures we have here, the set in the top is a set of 4 women jumping, and the set that we see in the bottom picture is a set of 4 glasses. Those 2 sets are considered equivalent because they each contain the same number of elements. If we look at these 2 sets, the set containing the letters C, A, and T, and the set containing the letters D, O, and G, those are considered equivalent sets because they both contain 3 elements. And you'll notice the symbol between those 2 sets. It's the tilde, the squiggle. That's the symbol that we use to represent equivalent sets. So if we write A with the tilde and then B, that means set A is equivalent to set B, and that's exactly how we would pronounce that. A is equivalent to set B. An empty set is a set that contains no elements. So you can think of an empty set like a box. If you think of the set as being a container, an empty set would be a container that has nothing in it. It would be an empty box. Now the notation we use for an empty set is either to use the braces, which denote a set that contain nothing in them, or you might have seen the symbol for empty set that looks kind of like a circle with a line through it. That also is an empty set symbol. A universal set is a set that contains all of the elements that we're considering. So there's a lot of elements in the world, and sometimes we want to restrict our consideration to a particular group of elements. That particular group would be called the universal set. So if you think about crayons, there are a lot of crayons in the world. But if we want to say that the universal set is just this set of 6 crayons that we have, then it's as if there are no other crayons in the world, that these are the only ones that we're considering. We have a special notation for a universal set, and that's the capital letter U. In fact, when we name sets, just by convention, we generally name them with capital letters. But if we name a set with the capital letter U, that specifically means that that set is the universal set. The complement of a set is a set that contains all of the elements in the universal set that aren't in a given set. So sometimes people think of complements almost like complete opposites, although opposite is probably not a really good word to use here. Opposite has some mathematical meaning. If you look at these two pictures, you'll notice that the picture on the left has some black and some white parts, and the picture on the right has some black and some white parts. And what's black in the picture on the left is white in the picture on the right. So these two pictures would be considered complements of each other. The notation for a complement of a set is to put a bar over the name of the set. So if we have a B with a bar over it, that means the complement of set B. So let's just consider some sets and think about these ideas we've just talked about. So set A contains the elements 2, 4, 6, and 8. Set B contains the elements 1, 2, 3, 4, and the 3 dots, which are called ellipses. The 3 dots mean that the pattern that we're seeing continues on. Set C contains the elements 1, 2, 3, 4, and 5. Set D contains no elements. Set E contains the elements Al, Ben, Carl, and Doug. And set F contains the elements 5, 4, 3, 2, 1. Now this may look a little bit strange. This is something called set builder notation. And set builder notation is a way of describing sets in what's considered a more mathematical way. So the way you would read this is that set G equals the set of all x such that x is less than 6 and x is a counting number. Now you may find that this particular notation is just a little bit tricky to work with. So if you rewrite what's being described after that vertical bar is the words such that, you may find that it's easier to work with this notation. So we're looking for all numbers that are less than 6 that are also counting numbers. In other words, we're looking at the numbers 1, 2, 3, 4, and 5 as elements of the set. So if we rewrite set G using a little more explicit notation, it might be easier when we're doing some comparisons of sets. So let's start with this question. Which sets are finite? Well, a finite set has a countable number of elements. And in this case, the sets that are finite are sets A, C, D, E, F, and G. We can count the number of elements in all of those sets. Now when you see this notation, we're looking at how many elements are in the set. So this notation means the number in set E. So set E contains Al, Ben, Carl, and Doug. So the number of elements in set E is 4. So the number of elements in set G, well, set G is written in that set builder notation, but if we look at 1, 2, 3, 4, 5, which is a different way to write set G, we can see that the number of elements in set G is 5. Which sets are equal to set C? Well, equal means sets that contain exactly the same elements in any order. So set F and set G are both equal to set C. Which sets are equivalent to set A? Well, equivalent means they contain the same number of elements. So since set A has 4 elements, any other set containing 4 elements is equivalent to set A, which in this case is set E. Now remember we had that notion of universal set. A universal set is a set that contains all the elements that we're considering. So let's say that the universal set contains the elements 1, 2, 3, 4, 5, 6, and 7. We know there are lots of other numbers in the world, but these are the only ones we're considering right now. And let's say set M contains the elements 2, 4, and 6. So what is the complement of set M? Well, that would mean every element that's in the universal set that's not in set M. So the complement of set M would be the elements 1, 3, 5, and 7, because the other elements of the universal set, the 2, 4, and 6, are in set M. So now let's think about some notation. Would these two things represent the same thing? So when we have brackets with nothing in them, is that the same as this particular symbol? Do they mean the same thing? In this case, the answer is yes, because both of them represent the empty set. And you can think of the empty set like a box that has nothing in it. The set is the box, and an empty set is a box that contains nothing. So it's almost like the notation with the brackets, that the brackets are the box. So is this true? If we have these braces, these brackets, with this symbol in them, is that the same as just the symbol itself? And in this case, the answer is no. Now, if you think about those braces as being the container for this set, then what we've got in the case of what's on the left side is we've got a container that contains an empty container, which is not the same as just an empty set. So it's as if we're saying a box that contains a box, is that the same as just an empty box? And the answer is no. So be a little careful with the symbolism. If you intend to write that something is an empty set, you either have to choose to use the braces with nothing in them or the empty set symbol. So let's talk about a few more definitions. Set B is a subset of set A if every element of set B is also an element of set A. Now, what that basically means is if we have a set, in this case it's set A, and we take some elements out of that set and form another set from those elements, then what we've got, our new set, is called a subset of the old set. The notation for this looks kind of like a sideways U with a line underneath it. So the way we would read this is B is a subset of A. So let's look at some specific sets, and let's see if we can use this notion of subset with these sets. Let's just answer some true or false questions. So I would read this as X is a subset of W. Now this is true if I can reach into W and take out of it everything that I need to make set X. And in this case, the answer is true. Everything that it takes to make set X is contained in set W. So is set Y a subset of set W? Can I reach into set W and pull out everything I need to make set Y? Well, in this case, the answer is false, because set Y contains the number 6, and that's not in set W. So I can't reach into set W and pull out everything that it takes to make set Y. Is set Z a subset of set W? Well, that answer is true, because I can reach into set W and pull out everything it takes to make set Z. And is the empty set a subset of set W? Now this one's a little tricky. You have to think about whether I can reach into set W and pull out everything that I need to make an empty set. And the answer to that is true, because if I reach into set W and don't pull any elements out, then I've created the empty set. And in fact, the empty set is a subset of every other set. Now, if we make a slight change to the definition of subset, we have the definition of proper subset. Set B is a proper subset of set A if every element of set B is also an element of set A. In other words, B is a subset of A, and B is not equal to A. So the one additional thing that distinguishes a proper subset from a subset is that in order to be a proper subset, set B cannot be equal to set A. The notation for proper subset looks like a sideways U. And what you'll notice in the notation is that we're now missing that line underneath that kind of looked like an equal sign on the bottom. So that's a little reminder to you that set B and set A cannot be equal to each other if set B is a proper subset of set A. So let's look at these same sets, and let's answer some true or false questions again. So first of all, is set X a proper subset of set W? Well, first we have to ask, is set X a subset of set W? And that is true. The second thing we have to check is set X equal to set W? And if it's not, then we do have a proper subset, so that's true. Is set Y a proper subset of set W? Well, first of all, Y would have to be a subset of set W, and in this case it isn't, because it contains that 6. So set Y is not a proper subset of set W. Is set Z a proper subset of set W? Well, first we have to check to see if set Z is a subset of set W, and it is. And the second thing we have to check is set Z equal to set W? And since it is not a proper subset. So the last thing we're going to look at, since we've just talked about subsets, is how many subsets can a set have? So in order to do this, we're going to make a table, and we're going to look for some patterns. And we're also going to start with a simpler case so that we can come up with a generalization of the number of subsets a set can have. So let's start by thinking of a set that has only one element in it. So if we have a set that just contains an element A, we could have a subset of that set that contains A, or remember, every set has the empty set as a subset. So the total number of subsets in a set with only one element is 2. So now let's make this a little more complex. Let's say we have a set with 2 elements in it, A and B, and we'll try to find all the subsets of this set. So we could have subsets that have 1 element, or we could have subsets that have 2 elements, or remember, the empty set is the subset of every set. So in all, we have 4 subsets for our set that contain 2 elements. So now let's make it a little more complex. Let's say we have a set with 3 elements. Well, we could make subsets from that set that contain only 1 element, or we could make subsets of that set that contain 2 elements, or we could make a subset that contains all 3 elements, and remember the empty set is the subset of any set. So in all, that gives us 8 subsets. Now what we're trying to do is make a generalization here. We want to know how many subsets a set has, if we know how many elements are in the set. So if you look carefully, you'll notice that we do seem to have a pattern going on in the number of subsets. So we're going to generalize this, and we're going to say, well, what if we have a set that has 4 elements? I don't really want to write all these subsets, but look for the pattern on the right side. So the pattern in the number of subsets is 2, 4, 8. Those are numbers that follow a geometric sequence. In other words, to get from one number to the next, I have to multiply by something, which in this case is 2. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So I could continue this. I could say a set that has 5 elements would have 32 subsets. A set that has 6 elements would have 64 subsets, but I need a generalization here. So let's say I have a set that has n elements in it. Well, if you look at the number of subsets, what you'll notice is that the number of subsets is always equal to 2 to a power, and the power is the same thing as the number of elements. So we can generalize this by saying that if a set has n elements, it's going to have 2 raised to the n power subsets. So what if I wanted to know how many proper subsets a set could have? Well, I could go through this same exercise of starting off with small sets and looking for how many proper subsets it has. And remember, proper subsets cannot be equal to the original set. So if I start off with 1 element and I look for how many proper subsets it has, a set with 1 element only has 1 proper subset. A set with 2 elements would have 4 subsets, but since a proper subset can't equal the original set, it would have only 3 proper subsets. A set with 3 elements has 8 subsets, but for proper subsets I can't include the subset that is equal to the original set, so I would have 7 proper subsets. And what you'll notice is that we still have that 2 to the n subsets, but we're losing one of those subsets because it's equal to the original set. So how can we deal with that losing one subset because it's equal to the original set? Well, we know that when a set has n elements, it has 2 raised to the n subsets. But if we want to know how many proper subsets it has, we would have to take away the one subset that's equal to the original set. So that means if a set has n elements, it has 2 to the n minus 1 for the minus 1 that's equal, proper subsets. So let's look at a specific case of a set that contains 6 elements, and let's ask ourselves how many subsets does this set have? Well, since it contains 6 elements, I know that it contains 2 to the 6th, or 64 subsets. Now that's a lot if we needed to list them all, but we're not being asked to list them, we're just being asked how many there are. And what if I want to know how many proper subsets this set has? Well, I know that the proper subsets cannot equal the original set. So there's going to be one of those subsets that is equal to the original set. I just need to subtract that off of my count. So the number of proper subsets is 2 to the 6th minus 1, or 64 minus 1. There are 63 proper subsets in set W. So that's an introduction to a lot of definitions that have to do with sets. We'll be looking at some set operations next and see what we can do when we're combining sets.